I would like you all to, first of all, go to this GitHub repo so that you're seeing this, this repo. Launch Binder, preferably in a new tab. You'll have this Jupyter notebook that I've set up. So in your Binder tab, you'll have this Jupyter notebook where you can evaluate what I'll be talking about. And please do follow along so that you can. It makes it easier to ask questions. And then at the end of it, after our 20-minute break, when we have the 1 hour session afterward, that 1 hour session will be devoted entirely toward these exercises, which you'll be doing on Binder. So if you can't log into Binder, you won't be able to do the exercises. Also, yours will look different because these are all expanded out. Collapsing them didn't look right on Binder. They have some old version of whatever. But I'll be, so it's all, it's all expanded out. If you ever get lost in that very large document, you'll see what I'm talking about here with some text on screen. Find in page for that text, and you'll be able to sync up where I am because yours is all expanded out. Okay, I think I'm ready to go. And I'll start talking about Python for data analysis. Should start with why Python? It's where the party's at. It's now the most popular programming language. And I seriously mean that as its major plus, that it's popular. I think the best argument for Python is this huge community of people who can help you, like online, Stack Overflow, lots of tutorials and such that you can watch, and people developing infrastructure. Chances are you've learned Python in a university course, and you'll probably use it a lot in your career. And that's whether it's a career in particle physics or out. And Python is not just a popular language just in general, but it's also especially popular for data analysis, which is what we do. So these are Google Trends searches. It's one of the ways that it somewhat quantitatively find out what the culture is on something. It used to be fairly recently, just some 5-10 years ago, that the language you would use for doing data analytics, like beyond physics, but in general, would be R. And then a lot of the early big data stuff was in Java. So early on, a lot of the data analytics was R and Java. But recently, Python has overtaken, well, both actually. And especially in machine learning, Python had already come into its own before this recent machine learning boom, so that all happened in Python. We usually steal photos from this excellent talk, slides from this excellent talk, but these Google Trends slides are separate. Why Python as a language? Well, it's one of a large class of languages in which debugging mode is always on. So, other languages like this are Lua and Ruby, and actually there's a whole lot of them. Somehow Python came to be the most popular one, and I think that's kind of a historical accident. So Python's the one we have, but really the technical thing that's different about it, different from say C++, is that it's got this debugging mode is always on kind of feature. So with minor exceptions, you really can't cause a segmentation fault or a memory leak. Basically, all of the errors produce a stack trace with line numbers. That's always on, it's always available. You can print an object. After doing that for a while, being in a language where you're debugging and you got these objects and there's no string representation for them, so you can't print them, it's just surprising. There are interactive debuggers, but they're kind of superfluous because the language itself is interactive. Instead of setting breakpoints, I usually put in raise exception just to get to that point in the code, and it's already interactive. And although long-running programs are slow, and that's going to be this cost of the debugging mode is always on, it starts up quickly. So if you're trying to solve some problem, you can get into the fix your code, test it again, fix your code, test it again, loop very quickly. Now this has a cost in performance. Most of Python's design choices prevent fast computation. Even in this class of debugging mode is always on languages, it's particularly bad. It's kind of weird that Python is the one because it's got all these strikes against it. I won't read them all. This is not necessarily a necessary cost. It seems that the Julia language could have the best of both worlds but Julia is not popular yet, so that's all I'm going to say about it. And yet, despite all of these performance limitations, and performance is an important thing if you're going to be dealing with large data sets, despite all of that, scientists with big data sets have made Python their home. And this was only possible because an ecosystem grew around arrays and array-oriented programming. I'll eventually define what I mean by array-oriented programming, but I mean it as kind of a paradigm, kind of like object-oriented programming, or functional programming, or imperative programming. They're not mutually exclusive, but there's such a focus on arrays that you could call it a different paradigm. So this ecosystem with all these different packages, kind of from the most foundational to the most domain specific, all of them are connected through arrays. This plot is actually a refined version of a frequently stolen slide from Jake Vanderplas's talk that I've linked up above, and we're in there. The Numpy authors included Scikit-HEP. Another thing I want to say about array-oriented programming, which admittedly I haven't defined it yet, it's also the paradigm of GPU programming. So if you're getting into GPUs, this style of thinking is also relevant. So maybe the slowness of Python pushed us toward this paradigm, but the idea, and maybe this is defining the paradigm, of dividing your work into some complex bookkeeping that doesn't have to be fast. So it's complex, you use the easiness of Python with this easy debugging. But that part doesn't have to be fast. And you separate that from some mathematical formula you compute on billions of data points. Make that separation in your code. In root instead of arrays, we use histogram. That's true. That's quite true. But this way is this separation, this mental way of organizing things, is also the right way to massively parallelize on GPUs. So we're pushed to it from the slowness of Python, but there's this kind of deep connection between what Python and Numpy people call vectorization, meaning you apply something to a whole array, and real actual hardware vectorization. There's a deep connection between those. And that's the last I'll say about GPUs. I have renamed this presentation from Uproot to Uproot Awkward to, I included a list of packages. Now I'm calling it a Scikit-HEP tutorial. Scikit-HEP is a collection of Python packages for array-oriented data analysis in particle physics. And yet we really mean it for particle physics, even though we called it HEP, high energy, does not describe all of particle physics. And we deliberated on that, but the other alternatives were worse, so we didn't go there. So this Scikit-HEP is an umbrella organization. It's not strictly, I won't talk about all the different organizations. The goal of this is to make sure that the packages work well together. They work well with a Python ecosystem beyond physics, and with the traditional HEP ecosystem. So that's root and the formats we use, popular generators, the collaboration software. And we also make sure that these packages are packaged well and designed well to minimize physicist frustration. So I'm the author of Uproot and Awkward Array, so I have the most to say about those. But the context is that these work with a suite of other libraries. The mindset is actually just like NumPy's figure here. You have a whole bunch of little packages that each do some part, and they know about each other so that they can work together. So it's not one monolithic thing. Sometimes people refer to doing their analysis in Uproot, but really they're doing their analysis in a bunch of things. So Python language features. I have heard that that Python is very new in your community, so I wanted to give some introduction to Python. But when I was thinking about it, there's so much to say about Python, and that really couldn't do an intro course here. And also, many of them exist. That's kind of the thing about Python being this super popular language. There are just a few language features, particularly slicing, that I'll talk about here. So in a standard Python intro, you'll learn about the control structures and when you can assign variables and you can do if statements and for loops and such. By the way, evaluate those on yours to make sure that your notebook is working. If it's not, reload your binder page. So these basic control structures, I hope you're familiar with them, but interestingly enough, they are less relevant in this tutorial because these things are what you want to avoid when you're working with large arrays. Explicit loops and explicit if statements, just like you avoid them when you do GPU programming. So we'll be focusing on operations that, that look like import some compiled library that's do computationally expensive thing to a big array. This is getting more toward what is array-oriented programming. Array-oriented programming, you do a lot of work in one Python statement. And what that one Python statement is doing is it's making some compiled code work. And this again is because array-oriented Python is about separating the small-scale complex bookkeeping. You do all your if statements and for loops and manage your files and arrange various things. And you want to separate that from the large-scale processing in the compiled libraries. Now, they're not actually going to look like this. Otherwise, we really wouldn't have much to say about Python because then Python would just be a gateway into these other. We actually do a lot of the logic on the Python side. It's not just call out to other library. The trick is for the Python side code to be expressive enough that you can express what you want the compiled library to do. So that the compiled library can be really general and you can put your logic in the Python. You don't have to split your world between actually writing a lot or writing any compiled code. The libraries are actually general enough that you don't have to leave Python. Most of that expressivity grew up around Python syntax for slicing lists. And actually, NumPy as a library had an outsized influence on the Python language development for how slices work in Python. You could kind of almost say NumPy is part of the core of the language, even though it's a separate library. So say you have some list. The single element access is just like C, starts counting at 0 and it's in square brackets after the thing. And actually this really common across a lot of languages. So by getting item 4, the value is 4.4. One of the special things Python does is that if you give it a negative index, it counts from the other side. And that's cute and it's nice. Sometimes it's very helpful. Running off the end of a list is an exception. It's not segmentation fault or data corruption. So that's good. We're in the safe world. And here's one thing that is getting kind of Python specific. This colon allows you to select ranges. So from index 2 to 7, get 2.2, 3.3, 4.4, 5.6, 6.6. Python is very consistent about these things, that the start of each range is always included, the stop is always excluded in both slices and things that are similar to slices. You can use the negative indices with the ranges. Out of bounds ranges, unlike the out of bounds single element, they're not exceptions, they get clipped. That's actually quite a detail. It's fine to not know that. There's a third and final argument to this start stops. You can also have a step, and that's for 1.1, 3.3, 5.5. We're skipping one. So you can look at all just evens or just the odds. And also you always have a easy way to reverse the list if it ever comes up. These start, stop, and step are exactly the arguments of range. So Python's very consistent about this. All right, so moving on to the next thing. In Python, the dicts, mappings like standard map, are just as important as lists. The square bracket syntax works in a different way, and actually C++ does this too. So now this is kind of like the index of this thing. And these have become common enough in most languages now that there's not much to say here. Okay. So that's pretty much all I'm going to say about Python, the language. because apart from function calls, arithmetic, variables, and assignment, which are the same in all mainstream languages, slicing is the only language feature that we need for NumPy. And I can move on to talk about NumPy. So NumPy is when we get started into this thinking one array at a time. Just sort of give an impression of what the NumPy library is all about. I took one of the cheat sheets. There are many of these. The library is kind of one major data type, np.nd array. That's an array, and a suite of functions to manipulate objects of that type. So this is kind of the high level view of the whole thing. You have arrays, which can be any number of dimensions, and each of the dimensions has an axis, and that's important. Awkward array uses axis quite a lot also. Often any of the things that you're computing, you almost always get a choice of which axis do you apply it to, the first, the second, the third, and like everything else, starts with 0. You have a bunch of different ways to make arrays, although you'll probably be getting them from your data files, from your Pico DST. And there's, you do arithmetic on them, the standard functions, but all of these functions apply element-wise, which I'll say quite a bit more about. And the slicing gets a lot more interesting because it's multidimensional. So I'll get into, I think, slicing first. Oh, no, before I get into that, NumPy adds the array-oriented concept to Python. And this is why so much of the ecosystem depends on this one library, because this library is so central, it might as well be part of the language. And in other languages that have had this kind of paradigm where you have arrays and most of the operations that you perform on the whole array with a big, one whole data set at a time, so one single value at a time. These languages, which all go back to APL, it literally stands for a programming language, because there weren't so many back then. You could title a book that way. They all have the same kind of mindset. This is a programming paradigm shared by all these languages. NumPy is different from these in that it's actually a library, technically. But another thing that's common among all of these languages that have taken up this paradigm is that they're pretty much all interactive data processing, which is exactly what we want to do. Slicing in NumPy. NumPy has the same slicing syntax for arrays as Python has for lists. I hope so. That would be kind of super annoying if it didn't. What are the color? Oh, what are the color? Lineages. S, R, and S plus are all very close to each other. I mean, R you might have heard of. This is data programming, data language. It's a descendant of S. And they just went down the alphabet. S was for statistics. IDL was used a lot in astronomy. It's what Python's replacing. This is Perl data language. Oh, actually, Perl data language is a library just like NumPy. That's why they're the same color. A lot of people go from MATLAB to NumPy. That's a common thing. And so a lot of astronomers go from IDL to NumPy. So that's kind of a trend that they're similar. Julia is kind of, it's not really so much an array programming language, but it has that feature. So that's why they're colored. Otherwise, I would make like a lineage tree, phylogenetic tree. Okay, so all the same slicing stuff that works on lists also works on arrays. But NumPy slices can operate on multiple dimensions because NumPy arrays can be multiple dimensions. This is my favorite way of quickly making a simple 3-dimensional array. I usually like to make the dimensions different sizes so I don't get confused about them, but that's because I'm mostly making examples, not doing data analysis. Okay, so here you can see this is how NumPy arranges it so that it's somewhat easy to read and somewhat easy to see the alignment of those numbers. And here is a slice where we're taking. When did you fill in all those numbers? Right here. A range And here's where I use the fact that this is interactive. Arange is one of these array making functions, and there are a lot. Yeah, so I made the, I went up to 30, 0 to 29, and then I reshaped it because, you know, Arange made a one-dimensional thing, and that just changed the shape to something that would work. So now, given this array, we can slice like this. This is slicing all 3 dimensions at once. 1 colon is we're dropping the first entry in each dimension. So we lose this whole thing because that's the first of the first entry of the first dimension. Then we lose, let's see, well, we lose both this and we lose these. And what we're left with is just an array of these parts, as you can see. Python lists do not do this. So I make a list that's the same as that array with the, take the array and say .toList. Now these are Python lists. Do that, and Python cannot do that because Python lists, they don't know the data type of what's in the list. It's dynamically typed, whereas the NumPy array does know the data type of everything in it. The NumPy arrays are actually quite the same thing as C arrays. They just have this Python object that addresses those C arrays. So if you have a mental model of how the memory is laid out for an array in C or C++, it's that same thing. Yeah, and then we can, I guess I covered up the example, but we can slice in one dimension and pick specific entries from another. I try to avoid scrolling too much when giving these talks. It makes people seasick. So I take the whole first dimension. That means I take this whole block and this whole block. And then I take the last corner of each. So there's 14 and there's 29. And that's how you can slice it to get that kind of array. And you know, when you think about it, you let your mind wander, you can really do a lot with this. You can, you know, imagine some voxels in n-dimensional space, some volumetric pixels. You can, with a clever slice, you know, do like any kind of thing. And in fact, the Hist library for doing histograms does that for histograms. So you have I have an example later on with a 4-dimensional histogram. We slice it and sum and, you know, do all this kind of things. And it's just this simple slice syntax that makes it really short and sweet. And then, of course, all of that computation actually goes out to the compiled library. That's how we separate the expression in Python from the heavy-duty work in the compiled library. And we didn't have to write the compiled code. And most importantly, the NumPy slices can also be arrays. You can, so here's an array that we are slicing. It's to the left of the square bracket. And here is an array that we're using as a slice. It's in the square brackets. And with a Boolean, the lengths have to agree. Actually, the whole shape has to agree. And everywhere that the Boolean is true, you let the values through. 0, 1, 2, 3, 4. And everywhere it's false, you don't let it through. So there's no 5.5 here. You get 6.6, don't get 7, you get 8. And you know, to spoil the spoilers, this is a cut. This is how we do cuts. There's also integer slices. So this does not have to be the same length. These indices are what it's going to pull from the array. So given the same array and give it these integers as a slice, at index 4, it gets a 4.4. At index 2, it gets a 2.2. I'm going to do index 2 again because why not? There's 2.2. So yeah, make random permutation arrays, which are, actually I should say what this looks like. This just is one of the things for creating arrays that gives you an array of integers. And by applying that to as a slice, we're always pulling out different things. So often, some complex, very, surprisingly complex problems can be solved by just creating the right index array and using it as a slice. So first application, this is kind of the core to particle physics, is, we do cuts all the time. A Boolean array slice is a cut. So let's say that you have some data representing primary vertices. Here I just made, also demonstrating the scale, I just made a million of them. So first dimension is million, second dimension is 2 for x and y. Normal distributed. So there's my fake primary vertices. Yeah, there's a million of them. And now let me make some fake trigger decisions, some random Booleans, false or true. And I've made a million of them. And by applying them as a Boolean slice, we have picked out the primary vertices for things that passed our trigger. And that's nearly half of them because of the way that I made 50% random numbers. The exercises will do that a lot. The exercising, so this is mostly, this first hour is mostly about introducing you to the whole idea so you know where to look. So observation, kind of as an aside, an integer array slice is more general than a Boolean array slice. For any Boolean array slice, you could have done it with an integer slice. And we can use a function called non-zero that looks for where all these Booleans are true, and then just make this indices that pass trigger, and apply the integer array to the primary vertices, and we get it the same way. So we've just completely reproduced what we did before, but now we're slicing with integers. So anything we can do with Booleans, we can do with integers, but integers are a lot more general than that. If you want to read my pretentious, I really got into this once, and it is in fact as general as function composition. So with that generality, you can do quite a lot. Many hard problems can be solved at compile time speed through NumPy without compiling a new extension module. You can just figure out how to make the right array of integers to pick out what you need. So we also have some particle physics-like applications of integer array slices that are not just the same thing as doing a cut. Imagine you had objects in two collections. The first collection is tracks, and here I'm using a NumPy structured array. This is an array with 3 fields. The first field I'm calling ID. The second field I'm calling PT, put in quotes. And the third is the shower ID, the ID in another collection. And here's that other collection, the showers. They have different lengths. Here there are 5 tracks and there are 4 showers. And you can pick out shower number 2. There it is. It's what I put in. You can pick out just the track ID of shower number 2. Then you could take that integer, that thing that we just determined as 4, pass that into the tracks to pick out track number 4. And then same thing, except we don't pick a single integer, but we let it be truth. We let this go for all of the integers in that array. And here we have in one go, for each shower, gotten the corresponding track. For each track, gotten the corresponding shower. For all of them all at once. And we'll be using that. And one of the examples we'll do that in the second hour. Okay, next basic thing to say about NumPy, and I'm aware of all this, they get shorter as we go along. Element-wise operations. All of the scalars to scalar math functions like plus, that takes 2 scalars and gives you 1 scalar back. Square root, sinh, all the transcendental functions. They can also take arrays as input and return an array as output. So the the mathematical function itself, the one that takes scalar, is performed element-wise. So you have some array, and we can do like array plus 100, and that adds 100 to every element in the array. This is a core idea of array-oriented programming. We can take a whole array plus another whole array and get an array back where each of these, they're aligned, and one by one they're added together. And since this alignment is so crucial to it, the lengths are important also. A lot of the error messages that you'll get are because lengths don't line up, especially when we get into awkward array, and it's not just the single length of the whole array, but the lengths of a bunch of lists within the array. So here, because then I take square root of these, and you can see just the perfect squares are the ones that come out as being whole numbers. So this is the part of array-oriented programming in Python that most resembles GPU programming. Because if you are totally in C++ and you're trying to get a whole lot of performance out of something, and you're trying to get that performance by doing GPUs, this is how you would do it. This is the technique you would use. And you'd just be doing it in a different language. So there's something really fundamental about this technique. Observation, these element-wise operations can be used to construct Boolean arrays for cuts. And this is what you'll be doing in the second hour. So let's say that we have some array of evens and odds. It's all the numbers going up to 10. Now, here is an element-wise operation. Taking the evens and odds mod 2, and here's another element-wise operation, equals. So actually, let me do this step by step. Element-wise of the mod 2 gives us those numbers mod 2, an array of them. And doing the second operation gives another array. And now these are all trues and falses because this is a comparison operation. So then we can apply this array of Booleans to the original array, or tilde, which is the opposite, logical not. And that all works because these comparison operators are also element-wise. So a range 9 less than 5, true, 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 false, 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 false. You can do logical operations with a single ampersand, a single vertical bar. So if you're coming from C++, not ampersand, ampersand, or bar, bar. And also if you're coming from regular Python, non-array oriented Python, the normal logical operators that you'd use in Python and or not, they do not apply element-wise. This is kind of the worst part of this. Fortunately, they raise an error to remind you, oh yeah, I'm not allowed to do this. But the worst part of this is that the operator precedence is wrong. You'd really love to be able to say, my cut is PT greater than something, absolute eta less than something, and you want that to be a cut. And unfortunately, that's wrong because this binds more tightly than what you actually meant. And so when you're using these logical operators, you always use parentheses. And I hate that, but that's how it is. Got two, these pseudo applications. I call them, I'm going to say pseudo applications because I make fake data and apply it. You have the idea of applying a mathematical formula to every entry of a large data set. And then this is part of a technique where you would just do that and then make a quick plot. And the argument that I would be making there is that making the quick plot is a lot like doing teach you draw. And we all love to do teach you draw at the beginning of an analysis because you can very quickly find out something about your data set. And then problem with teach you draw is that once you've made all the plots that way, then you have to remake them. You have to take all the expressions out of teach you draw and make a regular, for loop. The advantage of computing mathematical formulas with arrays and using them to make quick plots is that it's the same expression. You can copy it out and put it into into a large-scale analysis without having to change it. So that's the benefit, but I'm not really going to delve into this because I want to cover uproot, upward array in the 15 minutes I have remaining. But really, the most important concepts, we've just covered them. We'll be using those concepts. So into uproot. Uproot is array-oriented root IO in Python. So uproot is an implementation of root file IO in Python, re-implementation. So in this stack of dependencies, uproot does not use root. And that's been surprisingly helpful because then we've been able to install it and manage versions more fluidly than we would if like root NumPy and root pandas, which were actually inspirations for uproot. I had a lot of conversations with the author of root NumPy. The problem that root NumPy had by depending on root is that it would depend on some version of root, and everybody has like 2 or 3 copies of root on their computer. They're all different versions, and you use the wrong one and seg faults. So uproot is entirely written in Python, no seg faults. There's documentation, and because it's a re-implementation, that means that it doesn't have complete coverage. It can read most data types, and it's particularly good for simple data. So especially things like the Pico DST, that's fine. Those T-clones arrays, that's fine. As long as they are fully split as they are in the Pico DST. Uproot can also write simple data, and we're not covering that in this tutorial. It's a very new feature, but we don't use it here. All right, so sort of this is my terminology slide. So when I'm talking root terminology, some people have been working with root files a lot, and so they're fully immersed in this terminology, and some haven't. And so this is sort of, if you're unfamiliar with some words that I'm using, like T-branch and T-basket, this is where it comes from. So you have a file. Inside the file, there are directories, and you might have histograms, th1f. Those are like standalone objects in the directories. A T-tree is an object that has parts. Inside a T-tree, there are branches. These are kind of like the columns of a table of data. And Uproot's view of the world is to focus on like one branch, one column, because it turns that into one array. And with those arrays, you can go and use NumPy and all that. As sort of more of a technical matter, each of these branches are physically stored in little chunks called T-baskets. And the chunks are contiguous. And so this allows Uproot to be fast. But if you ever have performance problems, you start thinking about the T-baskets. If you're not having performance problems, you don't think about T-baskets. Just think at the level of T-branches. Okay. So let's get started actually doing something. So let's start by getting actually that Pico DST file that Dimitri gave me a copy. Start up Uproot, and you can open it with the uproot.open function. All of these links go to the documentation. It can be remote, as this one is. Maybe more often you want it to be local. But for this tutorial, I made it remote so that everybody can access it without having to download that gigabyte. Download it to Binder, which would be even more complicated. So yeah, this read-only directory object, it's a mapping like a Python dict. So that means there's square bracket syntax and this keys method. So if you're ever wondering, like, how do I ls in Uproot? In Uproot, you ls by saying .keys. And it's because you just think of it like a dict. Pretend the root file is a dict. And then just like a dict, you get a thing with the square brackets. So there's a T-tree. The T-tree is also a mapping, but now the keys are T-branches. This one has a lot of T-branches. They have a long form name, and it's also possible to refer to these without the sub-branch thing and details, but you'll just tinker around with it, you'll find that out. So there's a lot of branches. in Uproot, we see each of these as like independent objects. Any one of these can become an array. So these are our basic units. And there are a lot. So one of the branches is event, and that's what has these sub branches within it. So now you see there's no event slash anymore. These keys are just, literal, the string that you can put into square brackets to get the thing out. So it would have worked with the slash. It works without the slash if it's just like a dict inside a dict. Yeah, you play with it, and just this is kind of natural. These objects, they have a lot of methods and properties, so you can click through to the documentation to see them. And some of them, they get really low level. Uproot is actually a low level library, and it'll give you access to details you probably don't care about. But you have access just in case. One of these that's useful kind of at a high level is type name. It gives you a C++ type string, or Uproot's reconstruction of it. So this event, it's actually in each entry, it's a short array. These guys here, they're standard vectors, actually pointers to standard vectors. These are regular arrays. When you're searching through keys, unlike a dict, you can filter names, and that's very useful because there's a lot of these, and I didn't want you to have to keep writing list comprehensions in Python, which is what you'd have to do in order to filter these things out. So we have some convenient filter things. Again, look at the documentation. Yeah, so let's go through these filtered names to have the word event in them, filtered type names to have the word float in them. Go through all those keys, and for each one of them, print out, the name and the type. But then again, there's a function for that. So, ttree.show is pretty much the first thing you usually do when you're presented with a new file. All right, extracting arrays to actually get at the data, so you can do all the NumPy things with it. This t-branch array method reads an entire t-branch. So if you're thinking baskets, it's all of them from a file. So here we wait for a few seconds because this is remote and it's downloading. This is what the event ID is, and that's why it was an array. I don't know why it's structured like that, but actually it is. These all have length 1. For large or remote files, you can limit how much it reads using entry start and entry stop. So you can use this when you're exploring, like right now, what we're doing. You can stick in entry stop equals 10 so that it doesn't download as much, so that if you're still trying to figure stuff out, you can do so quickly. And then when you got everything figured out, you can remove that and let it do its long thing. You could also do it if you're constructing some parallel job. So Uproot does not do parallel processing, does root IO. But if you're building a parallel job and you want, this task is responsible for this range of entries, that's how you can do it. T-tree arrays, plural, this is the other method you should know about. It reads multiple T branches from the file. So it now, by default, actually, it'll read all the T branches from the file, which for this file, because it's remote and large, would take a really long time. So it's important to filter these, use filter name or expressions, see the documentation on what that is, say filter names in order to figure out which ones you want. You change your glob expression or your regular expression here to get just the ones you want. And then you can apply this so you don't wait forever while it goes and gets all 3 of those branches in one request. There, I did it. And now these are downloaded. You have these. So just extracting out something from that's immediate, whereas this part took a long time. Iterating over data in batches. This is what you'll want to do when you start scaling up your analysis, but you don't need it for the exercises, so I'm going to skip it with my 5 minutes left. Awkward array is for complex data in the arrays. So by way of introduction, you might have noticed that the arrays that were coming out of Uproot, by default, they were not Numpy arrays, they were awkward arrays. And that's because particle physics data frequently has variable length structures, and Numpy deals strictly with rectilinear arrays. This is the biggest pain point to try to use the whole Numpy, Pandas, all that stuff, ecosystem for particle physics. So, people would, truncate, how many particles they're looking at or something like that, and then get a truly flat n tuple before they could go and do the Numpy or Pandas stuff. Awkward array is an extension of Numpy to generic data types, and one of those is the nested lists. So see awkwardarray.org for tutorials in the reference documentation, but this is when I've been asked to give a one-page slide. This is my page. You can have an array with all this structure, like nested lists, these kind of record-like structure. And even though it's got all that structure, you can use it in these Numpy expressions. You can use these element-wise operations. You can use complex slices in order to, from this example, get an output that looks like that. Whereas the equivalent Python, if these were really lists and dictionaries, would involve a lot of opening things up and appending to the output to close it back down. And it takes much longer, use a lot more memory. So it brings this whole Numpy-like array-oriented programming style to generic data types, which we absolutely need in particle physics. So with 4 minutes left, there are things that I could talk about here, and mostly I want to get you aware that it's all here so that you can find it when you're doing the exercises. And you'll probably maybe be referring back to this part of the notebook. Slicing an awkward array. We'll go through a lot of the same examples as in Numpy, but now it gets more interesting because we can have arrays that have variable length lists inside them. And the slices are just a logical generalization of that. I introduced some of the special Numpy functions like awk.num in order to deal with slicing situations that get more difficult. Slices beyond Numpy, we want to still have the ability to do things like evens and odds, even though there's different length lists of them. We still want to be able to construct Boolean arrays of them. But now they have variable length lists inside, and we still want to be able to use the same kind of Numpy-like syntax in order to apply a cut, even if we have different numbers of tracks in every event, or different numbers of showers in every event, different number of tracks from showers. Talk about record arrays, making them and projecting them out. Making a record array is one of the things you need to do in one of the exercises. Records, just in your mind, substitute the word struct if you're from C, or classes. Combinatorics, because we often need to find pairs of particles that that come from a single progenitor. Searching for pairs event by event is the kind of thing that you don't have in Numpy, because in Numpy you don't have variable length lists of things. Vector, Hist, and particle show that there's a lot more libraries out there. Vector, which you'll use in the exercises for Lorentz vectors, so there's reference for it here. Hist, which we use only the smallest bit for the exercises, but this takes the slicing idea, and it's quite amazing. I'm just going to evaluate all of these cells. Pulling in some of your primary vertex data histogramming them in 4 dimensions so that you can, because I didn't put it. Histogramming them in 4 dimensions, and then slicing that 4-dimensional thing as you would slice NumPy in order to project out, X, Y, the Z component by summing over X and Y and summing over this M ranking. M ranking is a weird variable length thing. So it's really showing off, so your primary vertices really show off this this Hist package and all the things it can do with it. Particle is like a computable PDG. And there's just a ton of these little libraries that all do these, that each do this one thing. So, so I kind of gave you an overview that got shorter and shorter to the end, kind of like what they said about the pyramids in Egypt. It was a people of diminishing goals. They were originally going to make a big square building, and then got shorter and shorter as we got to the end. After your 20-minute break, you will all be working through translating the C++ analysis. This is using all of your Pico DST tools. Translating the C++ analysis into the equivalent Python. So you can see, oh yeah, if I was gonna do this kind of a nested for loop in C++, how would I do that with an awkward array function? I zipped past the ending bit about awkward array, but all of the information is there in the first half of this. And also there's lots of links to the documentation. Yeah, and I think usually you won't be translating analyses, because if you have like analysis code that works, why change it? You'd usually be starting new analyses. I just thought that doing an exercise on translating would make it very clear. This means that, and this means that. I guess I'll see you in 20 minutes.
I had a question on plotting. I've found that I like to work a lot with Uproot and Awkward because of what you're saying of these non-standardized length arrays. But I've also found generally I do things in PyPlot, and it doesn't seem to recognize awkward arrays more often than not. Yeah. Is that something that's being worked on right now?
There's two senses there's two senses of not recognizing. One of them where it just looks at this awk.array type and doesn't know what to do with it. That's been fixed in a later version where we've added a default so that any library that is calling an array that might be NumPy-like should be calling this one method, and we're implementing that method so it can it can change its awk array type into an NP-ND array on demand. So that's only part of it though. The other part is that the data you have is not shaped right to make a histogram. Because what a histogram needs is like a bag of data points, just a bunch of values, and they're unstructured. And what awkward array has is, the data type is not float. The data type is list of float. And we don't, now one thing that we could have done is if every time somebody tries to make a NumPy array out of your awkward array, we could have had it flatten, turn it into a NumPy array with a different structure than what it has. We decided not to do that because I think that would cause more bugs than it would help. So you're left with this thing that it wants a one-dimensional array, and it's got a array of lists. So you have to explicitly awk flatten it. And that'll come up in the exercises whenever we're plotting. Here also,
Okay, yeah, that's what I've been doing for and it's not that bad. It's just
Oh, okay.
every now and again, I write like I normally write and it throws an error, but I was just wondering if that's something that's in the works.
No, that's, I guess what I'm saying is that's kind of intentional.
Yeah,
Is
no,
that,
that makes sense, because if you were to flatten on demand and you want that structure, then it really probably does cause more confusion than it helps.
yeah. Also, this tutorial, so I went to the awkwardarray.org and I searched for plot. This tutorial describes several different things you might want to do, only one of which is flattening. So, when we've got some data and we want to make histograms of them, we're maybe just a little bit too loose about what exactly is one entry in the histogram. Because for some histograms, one entry is one particle. Sometimes one entry is one event. Sometimes one entry is one combination, like a candidate, which is made from two different particles. And those all have different multiplicities. And so if you are, if a hypothetical data analyst is not thinking carefully about which one of those they will have, they'll interpret the number of entries wrong. So actually having this formality that you're forced to flatten, then you know that you flattened. If you wanted one per event, like the best candidate per event, then you probably maximize over some goodness. You make some formula for compute goodness, closeness to the particle mass, optimize that, and like pick one element from each list. This one's just picking the first, so it's assuming you've already got them sorted. Aggregating, so maybe you want, maybe you want each entry to mean the sum over lists of variable length, or each entry to mean the mean over lists of variable length. Here's where I was getting at, maximizing, minimizing over a list. This is where you have some goodness criteria and you want the best, you plot the best per list. All of these plots have different meanings. And so, yeah, we wanted the you to have to explicitly do that because, so that there's no ambiguity about what this plot means. So, yeah, I felt that, but although usually, I guess 9 times out of 10, you want to flatten. And I've been feeling that pain too by doing, when computing this. Maybe what we'll do about that is add a method. So you don't have to say awk flatten of, but maybe it can be more convenient if it was typed, vertex data dot flatten. So that you try it once, it doesn't work, then you slap on a dot flatten and it does. Maybe that'll make it more ergonomic.
Thank you.
We also wanted to minimize the number of methods that these things have, because we have this mechanism for adding methods to an awkward array. And that's what vector does. It takes just these arrays of records of px, py, pz, and it imbues them with methods so that if you say .pt, it'll know how to compute that. So we wanted to leave that space clear. The namespace within an awk array is like valuable real estate where people might want to put domain-specific methods. We actually ran into a collision with that in awkward 0.x before the interface all changed, where the Cartesian product, it used to be called cross because it's a cross product. Well, like a cross of two lists, actually a Cartesian product. It was called cross, and then we had the 3-vector overloads, which also had a cross because it was, 3D vector crossing. And so that's when we learned that the method names, that namespace needs to be reserved. So when we do something like add dot flatten, we'll do that cautiously, with a lot of, that's not something that we just go and do easily. We have to decide, okay, this is valuable enough that we're willing to take this spot in the namespace.
So I'm looking at this iterating over data in batches.
Yeah.
Which is like right above section 4 awkward array. And looks like the final block of your code says like 4 arrays in pico.dsc.array,
Yep.
parenthesis filter name equals to, it basically asks for like the global momentum, either X, Y, or Z direction. But when I run over this thing, the only output it actually gives me is the X portion of the momentum, and it somehow magically just skips over the Y and Z direction. So I'm like,
they're all there.
Yeah, not.
I know what you're seeing, and I know why you're thinking that. Yes. No, that's all there. But the string representation of the awkward arrays are truncated. Truncated without like knowledge of what's in it. So truncated, not super randomly, but it shows you a little bit of the beginning and it shows you a little bit of the end. It is actually turning all 3 of those branches into arrays, and it's made the variable named arrays here is a record array of the X, the Y, and the Z. The branch names are so long, and the lists of data, because there's a lot of tracks per event, is so long that you only see the beginning of this, which is the X one. The Y and the Z, they're there. It's what the printout looks like.
Okay, I see.
Yeah, in the for loop, you could say, see where it says print len arrays, comma arrays. After that second arrays, you could stick in a dot fields. So it says arrays dot fields. And then what it will print, instead of printing the a truncated representation of the array, it will print a list of the 3 fields that are in it, strings, a list of 3 strings. And it'll be the rather long name of the X field, the rather long name of the Y field, and the rather long name of the Z field.
Okay. Yeah, I'm looking at it right now. Okay, I see.
Yeah.
All right, thank you.
Yeah, there have been other complaints about the string representation. There's so much data in one of these arrays. Like actually, there's so much data in a Numpy array that Numpy obviously, they have to truncate it too. You make a Numpy array with, with a billion elements. Not crazy if you've got gigabytes of RAM, and it will only print the beginning and the end of that array. So, give you a flavor of what kinds of things are in it, but it's not going to show everything. Obviously, it can't. With awkward arrays, we have that problem, plus also the structure problem. Sometimes there isn't enough space to not just show you the values, but also not show you the whole structure. So in a lot of these examples, we just print out the string representation of the array, which is of limited use. In order to really say what's in the array, we will take say array dot type, so that we can see the type string. But then we're only looking at the type string. Array dot to list if it's small, or if you can slice it to make it small. Dot to list will turn into Python lists, which show you the entire thing. So obviously, you don't say dot to list on a very large array; you'll be unhappy. We find ourselves having to do that in order to see the full structure. Because the string representation is so short.
Okay, thanks. I'll just play around with it and see like which one I like the best. Thank you.
Sure. Yeah. All of this is developed with a mindset that that you are available to tinker with something interactively. So actually, the only time you need to like understanding the string representation is if you are interactively tinkering with it. And at that point, you can say .type. You can look at, you can do as, bracket 0 close bracket in order to get the first one, and just print that, or say .toList for that if it's a record array and you want to see all its fields. .fields to see all of just the field names, which is less than the full type description. You kind of have to ask multiple questions to get a full sense of what this array is. Everybody is going to do the exercises, the very last section, which has a lot of subsections. So you might have to find on page exercises for translating in order to get to that point. So this is where you want to be. The exercises are not easy.